This assignment is our first look at implicit differentiation when an equation might not be solved for x. So we've already discussed a few of these. So this first equation is a circle with a radius of 3. We can see that it fails the vertical line test, which shows us that there are 2 points that share the same x coordinate. So no, this is not a function. Elements of the domain doesn't always have to be x's, but whatever our first variable is, elements of the domain are not unique. Might be one way of saying that. Fails the vertical line test is how you have probably been taught to practice that, so that would probably be acceptable. The second problem here, we do not have a plus or a minus there, so we only have the positive or principal root. So we know that that is only the upper semicircle. So that would pass the vertical line test. So if we squared both sides of this, if we wrote this in y form, you can see that this equation is related to the previous equation. So that's how you recognize it. So we started with the entire circle, and now this is a function because it is only the upper semicircle. So yes, this is a function. This is the upper semicircle from problem 1, is how they're related. So they're not equivalent equations, but they're certainly close to each other. All right, in question 3, if we have oil spilling on a surface, so consider dripping oil onto a floor, it would start expanding and the circle would grow here. So with time, so we want to introduce the idea here that our independent variable isn't always going to be x. So the area of the circle, as there's more and more oil on the floor, the circle would grow. So we're talking about the change in area with respect to a change in time, so that Leibniz notation. So remember, derivative of a came from delta a over delta t. So it's a slope, but at a specific instant in time. And in question B, it says, notice the radius is also growing as that amount of oil spreads on the floor. So we could represent that with a change in radius with respect to a change in time. So remember, we're not always in the xy world. We can use other variables as well. All right, in number 4, we're doing a derivative of an equation we've certainly seen before. A reminder that the d dx is the operation that says take the derivative with respect to the variable x. So with respect to x. So when we do the derivative on the y side, students say, well, that y just becomes part of the derivative. So when we take the derivative of y with respect to x, our resulting derivative represents a slope. On the right-hand side, when we did the derivative of 5x with respect to x, we just get 5. How come we don't get a derivative like this? Well, one thing I've suggested to students is to say, well, what if you did? What if you did get a derivative on the x? Because that introduces now our idea of a chain rule. If we did the derivative of x, it would be saying what's the change in x with respect to x? And of course, in no math class would we ever write something compared to itself. That value would always be 1. But that might be a technique that will save you from missing some chain rules in some future problems. So here is our summary for our new topic of implicit differentiation. Here we're asked to differentiate with respect to x. So we're doing a d dx operation on each term or on each side of the equation. So I could write a d dx in front of every term, differentiate with respect to x. And now our point here of what we were talking about a minute ago, by the way, this I should say is called implicit differentiation because we don't have to solve the equation for y. When it says y is equal to some function of x, that's an explicit function. This is implicit because it's not solved for y. So this one is explicit that I've just written. This one represents an infinite number of implicit functions. Remember, the entire circle isn't a function, but there are many functions we could get from the circle. All right, so if we did our derivative here, we would have 2x, and then could we do that chain rule on the x variable? The chain rule on the x would be that dx over dx term that we talked about. So we can see why we don't have to do that. So here I'm going to erase it. But that's a reminder that when we do the derivative of the y term, we need to now remember the chain rule on the y will always leave a dy dx, and that's going to stay there in every problem. And the derivative of a constant is 0. So we might do one more step here, and that would be solve this for dy dx, since it's easy to do so. Let's move the negative 2x to the other side, and then we would divide by 2y, and you can see that the 2's would cancel. All right, why did I start with the equation of a circle? Because we could verify this with what we know from geometry. So you've seen this in class already. Let me repeat what we know from geometry about the radius to a point. So if this is our point xy, we could say what the slope of the radius is. Notice that our rise is y and the run is x. So the slope of this radius is y over x. And now what did you learn about tangents in geometry? We know that the radius is perpendicular to the tangent line. I didn't draw that very well. Trust me that that's a tangent. So if we knew the slope of the radius, then the perpendicular tangent would have an opposite reciprocal slope. So we would get negative x over y. And compare the geometry solution to our derivative method. So nice that, again, we know we've got consistency. So if you needed the slope of the tangent to a circle, you could do that with geometry. When it becomes the slope of a tangent to an ellipse, that's when you will be using your calculus derivatives. Okay, and we've also seen this already in class, some practice with our chain rule. If we differentiate this y term with respect to x, we must remember that there will be a chain rule, dy dx. And if we differentiate an r term with respect to p, so we differentiate with the power rule, and then we cannot forget that there will be a chain rule on our variable, a dr dp. And the derivative of sine, I'll write down here where I have more room, the derivative of sine of a glob is cosine of a glob, and then the chain rule on that glob would this time be a dw dA. So remember that we have to do a chain rule now on variables. So the derivative of e to a glob is e to a glob, and then the chain rule on the z with respect to q. So the derivative of z with respect to q is our chain rule. Okay, so let's put this into practice here on some implicit problems. So here we're asked to find y prime. Our variables are only x and y, so what we're really being asked to find here is the derivative dy dx. So let's differentiate with respect to x. So this first step here, putting the derivative operator on both sides, we will often skip that symbol, but you'll know that we are differentiating with respect to x. So the first term doesn't need a chain rule. If we did, it would look like a dx over dx. And our second rule, our second term, power rule, 4y to the first, that one, when we differentiate a y with respect to x, of course, we get a dy dx. And on the other side, we have a 0. So again, we're looking for y prime, same thing as dy dx, so let's isolate this variable. So we could move the 3x squared to the other side and divide by the 4y. Sometimes you'll have a complicated equation that's not easy to isolate that derivative, but when possible, remember what this is. This is the formula for the slope of any tangent. To the original equation we were given, to x cubed plus 2y squared equals 10 at any point on that function. So at any xy ordered pair from this function, we now know how to find the slope of that tangent line. All right, so I think we've seen this one in class. Also, we want to differentiate with respect to time. So we're doing a d dt on both sides. And we talked about using power rule there whenever we have a square root and a d dt of a sine of s. So differentiate this term, 1/2 s to the negative 1/2, and then a chain rule on your variable ds dt, and then the power rule on the t squared. But now our derivative here, always think about it. Do we need a derivative on a t variable? It would be a dt over dt, so we won't worry about that. Our derivative of sine of x, so we didn't need a chain rule there, is what I just was saying. All right, back here on the right side, the derivative of sine, cosine of the same variable with the chain rule. On any variable that's not a t, you will have a chain rule. So here for the first time we have two terms that have ds dt. So let's put them on the same side of the equation. And you could write this as a square root of s in the denominator. Sorry, that's a 2. We're putting these two terms together. Move the cosine to this side so the two terms that have the ds dt will be able to factor it as a GCF. So we're going to add the 2t to the other side. So now we're going to write this in factored form. So we're going to factor that ds dt. And of course in your homework you'll be able to do this factoring all in one step. So should we clean this fraction up? Should we write this differently? Well, this is 1 over 2 square root of s minus cosine of s. So should we clean it up? That would be completely up to you. So what would you do? We don't like complex fractions generally, so we could multiply through by 2 square root of s. So that would be the optional algebra. But generally what we're interested in is using this slope formula at a specific point. So if we're just going to plug in a specific number. So I would only do that algebra if you need to in a multiple choice question. All right, so if we come to this next problem, and remember we could solve for y first, but there's more than one function here because we would have to do plus and minus the square root. So we might as well do implicit differentiation. And for both of these it says find y prime. So in other words, we're differentiating with respect to x. And we're doing a dx of 9. So this, I hope, is already becoming easy for you. So we'd have 18x. Should we do a chain rule, it would be on the x variable when we're differentiating with respect to x. Not needed. But on the next term, you have to remember that y represents a function of x. So we do need a chain rule here. So dy dx and a derivative of a constant. So now we can solve this for dy dx. Move the 18x to the other side and divide it by 2y. So can I do that quickly? 18x over 2y, I can cancel to come up with this. Now if you wrote it as y prime, dy dx and y prime are interchangeable notations, so that fits the directions. Okay, here we have a power rule and we want to do the derivative. So I'm going to write this on both sides. Feel free to skip right to the next step. I think you've now had enough practice with this. 1/2 x to the negative 1/2. I do not need a chain rule on the x term, but I do need to remember to do the chain rule on the next y term. So we have a dy dx and a 0 on the right side. All right, so how should we clean this one up? Let's be a little more careful here. What you might want to do here is multiply by 2 first, since we have halves in both of these terms. So, and then I could rewrite these as 1 over the square root of x and 1 over the square root of y. And on the other side, we would still have 0. And then we would have 1 over square root of y, dy dx. We would move the term with no derivative to the right-hand side. And then I would multiply both sides by the square root of y. So dy dx. So we could write it this way, or when you're actually finding the slope, you might say, well, how about if I do the ratio of y to x and then do its square root, since those are both to the 1/2 power. So it would depend on what numbers you're putting in here. If y is divisible by x, then I would choose this order of operations. If y is not divisible by x, then I would choose the first version. So those are equivalents. And this next one, we're going to differentiate and then find the equation of the tangent line. All right, so this is an ellipse. We've got positive x and y squared. Implicit differentiation, you can definitely see that this would not be easy to write as an explicit function. So here our implicit differentiation will require a product rule on the middle term. So we have to be very careful here. So I'm differentiating with respect to x on both sides. So we'll get a 2x. And now let me switch colors here for the product rule. We're thinking of this. Remember our product rule in class, we started with uv. So the product rule is the first term, x, times the derivative of the second term. The derivative of y is 1, but don't forget the chain rule, dy dx. And then plus our second term, y, times the derivative of the x term. That would just be a 1. It would be a dx dx if you did a chain rule. So there's our product rule for that middle term. And then the derivative of the y squared term is 2y dy dx. And on the right side, we have a 0. So we'll have two terms that have a dy dx. So this term right here and this term right here, I'm going to keep those on the left-hand side of the equation, and we could write it in factored form if you wish to save time. And these other two terms, the 2x and the y term, we're going to move to the other side. So whether you keep a negative out in front and use a plus sign, or whether you make them both negative, certainly up to you. The reason I might like it out in front here is I can see what I'm going to do in my final step is have a binomial divided by a binomial. Neither of those, while they look quite similar, neither has a factor. So we would leave our slope formula this way. So this is how we will find the slope of any tangent. So now we're ready in this problem to use our derivative. So we want to find the derivative of the tangent to this equation, and we already are given the xy point here. You can verify that it works. If you put 1 in for x and 1 in for y, can you verify that this is a solution point? 1, 1 is our point of tangency. And our slope, we're going to use our derivative formula. So you might now use this such that bar, and then here we're going to say what we're substituting into our derivative. So this vertical such that bar is nice notation when you come back to read your work later, you'll remember what you're doing. We're taking our derivative formula, and of course you could do this arithmetic more quickly, but I'm going to substitute in 1 for x and 1 for y. So our slope turns out to be a 3 over 3, so our slope turns out to be a -1. And now we're ready to find that equation of our tangent line in point-slope form. So we know our point of tangency, and we know our slope. So y minus 1 is equal to our slope times x minus 1. And that's perfectly fine. Leave it in point-slope form. If it's a multiple choice question and you need to rearrange it to slope-intercept, that would be fine. But this answer is perfectly acceptable. So there's our first introduction to implicit differentiation.